Welcome. I'm David Biesack, VP of API Platforms at Apiture. I'm responsible for the design and architecture of our APIs and our developer experience. As you can guess by our name, Apiture is an API company, but we're not an API tooling vendor. We build banking APIs and customer experiences on top of those APIs. And we've embraced openapi from the beginning. Today, I want to talk about what it means for a specification like the openapi specification to be open. And when I say openapi here, I'm referring to the openapi specification, but I'll use that as an abbreviation without saying it all out every time. There are many interpretations of open. For example, the openapi initiative and the technical steering committee use an open process for defining openapi. And openapi is published as open source. Those are important characteristics of openapi's openness, but I'm going to talk about a different specific aspect of openapi's openness. Many of you are probably aware of the SOLID principles. SOLID was originally coined for object-oriented programming, but it applies much more widely in software. The 5 SOLID design principles listed here are intended to make software designs more understandable, flexible, and maintainable. The open-closed principle says that software entities should be open for extension, but closed for modification. And that is what I'll be speaking about today, how the openapi specification is open to extension. openapi supports what are called specification extensions. This is additional data that one can inject at many places within an API definition document to add additional information. These extensions begin with the pattern name prefix x-. The example they gave here is x-internal-id. But I want to make a small, important correction to this definition. It says additional data can be added to extend the specification at certain points, but this should really read additional data can be added to extend the API definition document at certain points. This is an important distinction, and since this is the entire purpose of this presentation, I want to be clear on what extensions are for. We're not extending the openapi specification itself, which is fixed at a specific published version such as 3.0.3. Specification extensions allow us to extend the API definition that is written with a specific version of the openapi. Of course, there's a long history of extensible systems and frameworks. Even systems of government can be extensible. So while it's not novel, openapi could have been devised without an extension mechanism. I don't think it would have been quite as successful if it had been published without extensibility, however. So it's important to give credit to the creators and maintainers of the openapi specification for understanding their audience and anticipating their needs for applying the open-closed principle and providing a way to extend API definition documents. So there's lots of reasons why one might want to extend an API definition. The primary one is to provide information for tools to process and analyze your API. And it's important that you try to add this information in places other than just in your description strings. While automated natural language processing is certainly improving rapidly, it is orders of magnitudes more difficult to extract desired behavior from those description strings. English or other natural language prose descriptions are still very imprecise. It is much better to codify intent and metadata with structured data rather than natural language. openapi definitions are structured JSON or YAML for a reason. Thankfully, they're not extensible markup language documents. openapi uses JSON because it is designed to be consumed by people and by software. Thus, if one intends to extend an API definition, one should likewise do so using that same substrate of JSON data, not imprecise natural language. A very common class of extensions provide metadata for the API implementation. For example, API gateway deployment configuration, or object relational mapping hints like database schemas, database column names, and constraints. But be sure to not expose such implementation details in your published OpenAPI definitions. So let's talk a little bit about using specification extensions. And specifically, I'll talk about how Aperture uses them. But first, I want to give you a quick overview of how these fit into our API lifecycle. We begin with source code that has an OpenAPI file in its own source repository. The build for that API definition repository runs YAML and spectral lint steps, then runs our internal OpenAPI annotation tool, which reads all these annotations, which is our term for the implementations of specific specification extensions using an x-apiture prefix to generate an output file. This process also generates client SDKs for the resulting API definition. We publish that output into our versioned artifact repository, where the implementation tool projects load that definition and perform a second stage of code generation for that specific API service. A final filter also transforms this output OpenAPI definition into the source for publishing the API documentation. So we use a number of extensions. There's 10 or 12, but I'm going to talk about 3 of them today to give you an idea of the variety of things you can do with extensions. The first extension that I'll talk about is our x-apiture-links annotation. Now, Aperture APIs use HAL, Hypermedia Application Language, which provides for embedding links and hypermedia in resource representations. While OpenAPI 3 has some support for describing links, that support is limited to just response objects. At Aperture, we wish to embed and document the links in response objects and in request objects. In a request, a link expresses a desired relationship between 2 resources using their natural resource identity, which is their URI. For example, when a customer creates a transfer between 2 accounts with our Transfers API, the client can select the source and target account and track their URIs. Then the create transfer operation accepts a request that contains links to the source account and the target account for that transfer. Likewise, when you fetch a transfer, the response includes those same links to point to the source and target account for that specific transfer. Defining links in resource schemas allows for uniform representation regardless of whether the resource representation is used for a request or a response. Thus, we augment our schema definitions with the x-apiture-links annotation. Our tooling can then inject those compatible links into OpenAPI 3.0 response object definitions, so other OpenAPI tools can process them in the expected manner. Our tooling also processes the annotation and injects a table into the schema's description directly in line, so that other API doc tools will also show the documentation for those links on that schema, even if one does not use our published HTML documentation. It's critical to note that this additional documentation is derived from the structured data in the extension. We apply the dry principle, don't repeat yourself. There is one source of the truth, and it is the API definition document. We derive documentation from this, but also generate code from these annotations. And here I'd like to give a shout out to Mike Ralphson of Mermaid Software for the Widdershins and Shins tools, which we use to generate our API documentation. You can find those tools on GitHub. Like other good software, it applies the solid principles and is extensible by end users via custom templates and code callouts. The second example of how we use specification examples is the x-apiture-errors annotation. Aperture APIs use a rich API error description format. Each error response can have a type identifier, which provides more information beyond the specific HTTP status response. Here, a transfer operation can fail with a couple different error types, including an error type of transfer amount below minimum. Each error type is an identifier, which refers to an error definition located elsewhere in the API definition. And errors can thus be reused across multiple responses. Errors are defined with an x-apiture-errors annotation at the root or the components of the API definition. Each response that lists errors refers to these error definitions by name. Each error definition has three main parts: a description string that describes the error, a remediation string which is included in the error response. The remediation string assists the developer in resolving the error. We don't just tell you what happened, we also tell the developer how to correct that particular error. This is most useful during client development and debugging. Finally, an error definition can have optional attributes described by a JSON schema, which provide further details about the error instance. And these runtime attribute values are included in the error response. So a transfer amount below minimum error will include an attribute called minimum, which is of type string, which has a numeric value representing the minimum amount for a transfer. As with our links, our API pipeline enhances the API definition so that each response's description also includes a list of error types that may be returned with that HTTP error response. We can see that here for 400, there's two different errors that are listed, and this comes directly from the error type annotation on that response object. Each of those types in this documentation are links to the error type's description and definition located elsewhere in the API documentation. And this is what that looks like. All the error types are listed at the top of the document. Our API and pipeline generates this from the annotations and injects it into the info.description text in the API. Beyond just the documentation, though, we also generate additional files that are useful for developers. If you encounter one of our errors, you can quickly look up the documentation and other information about that error on our servers. So we publish an HTML file, which is, you can see a snapshot of one of those here that describes the error, the description, the remediation, and the schema. It summarizes that for you. But we also generate an error.json file, and this is a structured JSON document with a published schema. And we also publish a schema.json file, which is the JSON schema for the attributes associated with that error. And again, all of this is derived from our OpenAPI definition document. The final example I'd like to share with you is our x-apiture-traits annotation, which augments operation objects in our OpenAPI. Our collection resources have a flexible collection filtering parameter. For example, our documents API can filter the document collection based on the type or category of the document, or it can filter on the issue dates for documents such as account statements. The latter property filter supports relational operations, less than, greater than, less than, equal, etc. One can search for documents between two dates using a flexible filter expression of ands and or comparisons. The x-apiture-traits extension on an operation describes how a collection can be filtered. The in operation is for set containment, so one can search for documents whose type is in a list of target types, for example. These annotations are then pushed down into the implementation in our services to allow the service middleware and the code generation there to validate query parameters automatically, not only for correct syntax, but also for correct use. And they can reject invalid requests before they make their way down to our manually coded controllers. For example, we don't allow the greater than filter function on the document type or category, nor do we allow the in operation on start on or end on dates, because those types of filter queries don't make much sense. Client applications which wish to implement expression builders for these filters can also use this metadata to guide and constrain the expression that they build. And of course, we inject documentation into our API definitions from these annotations so that the documentation shows up in the API doc. And you can see here that the description for this filter parameter lists the filterable properties and the functions that you can use on those particular properties. So this is a good example of how Aperture uses some of these extensions. Let's take a look at how others in the industry use extensions as well. I want to point out a registry, Mike Ralphson at Mermaid Software, the same folks who gave us widdershins and shins that we use for our API doc, has a repo called openapi specification extensions. And it contains an index of a whole bunch of different vendors who provide API extensions to allow openapi to integrate with their systems. And we'll look at a couple of those in just a moment. Also, they have a repo called Swagger++, which has a list of useful extensions to be added to an openapi 2.0 document that can support converting between openapi 2 and openapi 3. For example, you can use an x-deprecated tag to mark not only operations, but also properties and schemas as deprecated. The deprecated flag only applies to operations in openapi 2.0. It's not allowed on parameters and schemas as it is in 3.0. But by using the extension, you're creating a bridge between 2.0 and 3.0 that can aid this conversion, and tools can take that annotation and inject a deprecated tag in an openapi 3.0 output document. OpenAPI.org also maintains a registry of extensions, but this is pretty nascent at the time. There's not much content there yet, but hopefully we'll see some more stuff coming soon. So here's a couple of those examples from that larger inventory. API-matic documents a whole bunch of extensions, and here's one of them. They have an Xcogen settings extension that's used in a document in the info block that can control code generation, and there's a whole bunch of options that are defined there. And their documentation describes what each one of these properties are. Another example is the DocuSign API. They can add extensions into their schemas in the definitions section, and here they're referring to openapi 2.0. They're really talking about schemas. And so there's an XDS category extension, which gives a name to the definitions resources category. So you can categorize all of the schemas or definitions in an API. And this value will match the name of a category defined elsewhere in the API. There's also a definition name which is used for code generation. And that's a pretty common type of thing that you'll see. Both of these examples use a vendor name in the name. So X-DS is an abbreviation to indicate that this is a DocuSign extension. One thing I want to point out is, as I mentioned, the value of having extensions in the API definition is that it treats your OpenAPI as a document. The API handyman, Arnaud Laure, published a multi-part series on using the JQ JSON query tool to process OpenAPI documents. And I recommend taking a look at this. It's pretty useful and helpful. JQ is a really powerful command line tool for filtering and manipulating JSON documents. And it's got a powerful and concise syntax with transformation pipelines and filtering and conditionals and all kinds of other things. It's a great tool for transforming one JSON document to another, or extracting data out of a JSON document and doing other things with it. And again, this just emphasizes how we can treat an OpenAPI document as data to do all kinds of things with it. And then it extends to using extensions. So let's talk next about the implications of extensions. So as I've mentioned, these extensions are very powerful and you can do lots of things with them, but with great power comes great gotchas. And the first thing I want to mention is directly in the OpenAPI specification, where they note that these novel extensions, quote, may or may not be supported by available tooling. So that's a really big caveat that you have to be aware of. If you're going to be using lots of different tools, the tools out of the box are not going to recognize your extensions that you may add to your definition. So that means really that the API community lacks kind of consensus on what extensions are useful and can be used. Each vendor defines their own, and there's not necessarily any consistency between extensions from one vendor to the other. There may be a lot of overlap, or there may be even conflicting types of data. So there's no real governance around all these extensions. Everybody's free to create what they want. So that's good, and it's also a risk. You just have to be aware of that. So there's really not a robust registry or shared repository for these extensions. Mike has a good index of some vendor extensions, but again, they're not really designed for reuse across those vendor environments. Another thing to be aware of is that these extensions are part of openapi. And even though openapi uses JSON schema, the JSON schema specifications, the latest draft is the 2019-09 draft, do not formally support extensions with these x- prefixes. So the x- convention is just for openapi. It doesn't extend into JSON schema. So you have to be aware of that. If you're using additional tools to process your schemas, those tools won't support extensions, and it may even break some tools if they do stricter parsing and they don't recognize additional elements inside the JSON schemas. And finally, the last thing I want to warn about is potential deviations from openapi at 3.x, etc. What you want to do with extensions is enhance your definition, but try to avoid creating your own forked version of what openapi means. And when I said earlier, try to stay within openapi, this is what I'm really referring to. We want to avoid creating ideas or concepts with extensions that are really better suited towards putting into openapi. They're good for bridges. If you've got an openapi 2.0 document and you want to convert to 3.0, extensions are great for that, or for documenting links or deprecation, things like that. But be wary of creating entirely new descriptions of APIs that are incompatible with openapi. And to finish, I'd like to offer a few tips if you're going to use openapi extensions, and I hope you will. First, my strongest recommendation is to use these extensions to transform a source openapi document to an output API document. You can use annotations to create concrete and concise definitions of transformations without having to manually code that, and then you can use tools to expand those extensions into much more robust features. But if you stay within the API definition, that's where you get the most benefit. I also recommend that you define a strict JSON schema to validate your extensions, and then use Spectral to enforce those JSON schema conformance within your extensions. And you can extend Spectral, as I mentioned before, by writing your own functions and rules that apply, and then Spectral can enforce those schemas, and it fits within the rest of your pipeline where you're trying to lint your openapi definitions. Also, as I mentioned earlier, be sure to strip out implementation details when you take your openapi document and publish it publicly. So this is if you're going to publish your API documentation on your website, or you're going to return that API document from inside your service via some GET operation. You want to remove any kind of internal implementation details that would otherwise become sources for attack vectors against your services. Finally, these API extensions can be coded with either primitives like Booleans or strings or numbers, or you can define them as objects. And I recommend you consider defining them as objects, even if there's only one value at this point, because objects are extensible and we like extensible things. So thank you for paying attention and watching. I hope you've gotten a good sense of why specification extensions are valuable and how you might use them in the future, and also how to avoid some of the pitfalls. Like all API development, planning educating yourself, and careful consideration of design and engineering choices are key to successful adoption of OpenAPI and the OpenAPI specification extensions. Thank you and good luck.